right, it's a cold day out here in the physics neighborhood. We had a cold front come through a couple of days ago, and it's still in the 40s. So we are not even able to take a little walk outside. Well, but here we are. We're doing AP Physics C, we're doing mechanics, and we're doing one that I think is kind of important. This is going to be potential energy functions and their relationship to forces. My name is John Frensley. I teach at Prosper High School, which is about 30 miles north of Dallas. This particular discussion on potential energy and forces is probably pretty well aligned with AP Physics 1 if you want to tell your AP Physics 1 buddies. There's one slide that has calculus on it, but really everything we're doing is reasonably within the scope of something that an AP Physics 1 student might be able to do, maybe a little bit above, but it's good practice, right? Okay, so let's start with a warm-up here. So what you'll see here is I have a potential energy function in my purple graph. So we have an object with a mass of 9 kilograms. I feel like that's going to be important. It's initially at this position, x equals 0. Whoops, I did not mean to start the timer. It's moving to the right. Now, this object is subject to just one conservative net force, or just the net force is going to be conservative. We'll find out what that means later, so that its potential energy is given by this function. Now, I gave you the function, but really I gave you the graph. I'm going to give you a hint. You don't actually need this function right here because the graph is going to do what you need for it to do for you. So I'm going to want you to answer two things. One, or A, what's the slowest speed that this object needs to make it over the hump and make it to 6 meters, right? So what's the slowest speed that'll get it over the hump? And then I want you to describe in words, how is the acceleration's magnitude changing from the top of the hump 3 to the bottom of the other end of the hill, which is 6, right? So you're going to do a little math and you're going to do a little words. You don't need to use this function because the graph will do it for you. So let's go ahead and give you 3 minutes on this. On your mark, get set, go. Okay, that's enough of that. All right, just like most of our discussions, I'm going to show you the answers a little bit later on, but first let's have a look at what we're going to look at today. We're going to explain what makes a force conservative. We're going to name some conservative and non-conservative forces. We're going to qualitatively, that's with words, describe the motion of an object. If we're given its potential energy function, we're going to do some quantitative stuff. Today's math is going to be pretty easy. I've heard that on this particular exam, if there is any math, then the math is tiny, might only be integers, and you're going to only do math in order to support some kind of larger argument. Does that make sense? Okay, so we're going to practice that idea here today. So here's what you need to know. All right, so what's a conservative force? It's a force that conserves mechanical energy. And what is mechanical energy? It's kinetic plus potential energy. So if a force changes kinetic to potential or potential to kinetic, it's a conservative force. If the force changes some other form of energy to kinetic or potential, adding to the mechanical energy, not a conservative force. If a force takes away mechanical energy and changes it to some dissipative form, you know what I'm talking about, not a conservative force, right? All conservative forces have a potential energy associated with them. So think in your mind, which potential energies have you heard of? Have you heard of gravitational potential energy? Then there must be a force associated with that gravitational potential energy called gravitational force, right? Oh, is there spring potential energy? Then there must be a force associated with that potential energy called the spring force. Those are conservative forces. A conservative force's magnitude and direction only depend on where the object is located. So all you need to tell me is where the object is. You don't have to tell me how the object is moving or accelerating in order to find out how the conservative force is exerting force, right? So let's think of a non-conservative force. How about friction? Have you heard of friction potential energy? No, because friction's not a conservative force. Friction's direction depends on where the object's moving, right? Not a conservative force, right? And then this is the big thing that makes a conservative force conservative and leads to a lot of theorems that we're not going to say today, but we're going to use accidentally. The work done by a conservative force depends only on where the object starts and where it ends, not on the path taken between them. So for example, if I move an object from this point A to this point B, and I say how much work is done by gravity, the answer would just be mg times the delta y between these 2 points. Doesn't matter whether I went straight there or over and up or up and over, the work done by gravity would be the same number of joules no matter how I got from point A to point B. The work done by me, on the other hand, might be different because my muscles do not exert conservative forces. If my muscles exert a conservative force, then doing this would change potential to kinetic energy, but then you could push back on my hand and then I would gain potential energy. Like I would be getting fatter right now with more calories for doing that. It doesn't work that way. Humans do not exert conservative forces. Three conservative forces. The first two would be for mechanics. The gravitational force only depends on where you're located. Notice the R in GMM over R squared. The spring force depends on how far the spring is stretched. So there's a position there. For those in electricity and magnetism, the electric force from Coulomb's law is also a conservative force because there's such a thing as electric potential energy, right? Here's some non-conservative forces are good for friction. Friction depends on how the object's moving, not just where it is. The drag force from air depends on how the object is moving and how the air is moving too, not a conservative force. There's no drag potential energy. For those in electricity and magnetism, the magnetic force actually is not a conservative force. That force depends on where or the direction of the object's motion, right? QVB, if you've studied that. That is not a conservative force. There's no magnetic potential energy the way there is for electric potential energy, at least not for individually charged objects, right? Okay, so what's the relationship between force and potential energy? This is a big one. It's not on the formula chart, and it's pretty important. So I'm going to ask you to know it or write it in your notes that you're going to use on this year's exam. The potential energy can only depend on an object's position, right? So you'll notice all potential energies you ever come across have some kind of position variable in it, like mg height, right? mgy, or 1/2 kx squared, or GMM over r, negative GMM over r for universal gravitational potential energy. KQQ over r is the electric potential energy. All of those things have some position variable in it, right? So force is the derivative of potential energy with respect to that position. And there's a negative for direction. So the negative indicates that the direction of the force is always toward a lower potential energy. If you don't put the negative, then you're communicating that if I put a ball on a ramp, it will speed up uphill. That doesn't make sense. okay? Instead, the ball accelerates and is forced downhill toward lower potential. So it's important that that negative be there to tell you that the direction of the force is always downhill toward lower potential energy, right? So here's a quick derivation showing that F is negative derivative of potential energy, right? So here's a little proof. So I'm going to start with the definition of work. Here in AP Physics C, we have work as the integral of force as a function of distance, right? But there's also something called the work-energy theorem that says that work is how much kinetic energy you gain. So when a force does work, it's giving an object kinetic energy, or negative work would be taking away the kinetic energy. Now, here's the line that's the key line right here. If you have only conservative forces acting, then the kinetic energy you gain and the potential energy you lose have to balance out, or the kinetic energy you lose, the potential energy you gain. If non-conservative forces act, then some energy is coming in from, say, a chemical type of potential energy. That would be like when you step on the gas in your car, or energy is going out to thermal or sound energy. That would be like if you push the brakes in your car, right? But if only conservative forces act, then only kinetic turns into potential, potential turns into kinetic. There's no other types of energy involved. So their changes net to zero. So let's subtract delta U to the other side. Now I'm going to say that delta K is the same thing as work, because I just said that up here. I'm going to change delta U into U minus the U that you started with. That's what delta U is, the U you have right now minus the U you started with. So you need to pay attention to the U you started with and the U you ended with, okay? I'm talking to you. Now, I'm going to change my work back to integral of force with respect to distance, right? But now I'm going to bring the integral sign to the other side, which means that I'm going to differentiate both sides. So taking the derivative of both sides, the derivative of an integral is itself. The derivative of U, or should I say the differential of U, is du, and the initial U is a constant, because that initial U is now in the past, and you can't change the past. So whatever's in the past is now a constant. So the derivative of a constant is 0. Then I divide by dx, and I get forces negative du dx. So if you're looking at a potential energy function, take the derivative and slap a negative on it, you got the force at different places. Or if you're looking at a graph, you're going to look at the slope of the potential energy versus position graph. The steeper the slope, the more the force. If the graph is sloping up, the force is downhill. If the graph is sloping down, the force is downhill. The force is always directed downhill toward lower potential. So what I'm going to do today is I'm going to show you some examples with potential energy graphs. And the way I handle potential energy graphs is this. I treat the potential energy graph as if it is a physical, real-life roller coaster track that the object is riding on, like a little cart or a little marble. Now, remember, potential energy is an abstract idea. There is no actual physical track that the object's on, but I imagine it as if it was. So if you show me a U versus displacement graph, I'm going to see it as if it's a literal metal or wooden track that I can set a marble on. And I'm going to ask, what's the force on that marble? What's happening to the velocity of that marble? And whatever the answers to those questions are going to be the correct answers, right? So the steeper the graph, or the steeper the track in my mind. The graph is on the page, but the track is in my mind. The greater the force, the greater the acceleration. The direction of the force acceleration is always downhill. So if the track is like this, force is that way. If the track is like this, force and acceleration are that way, right? The higher the object is, the slower it goes, because the higher potential energy is less kinetic energy going slower. And then I'm going to talk about this. It's a line that you can draw on a potential energy graph. It's called the total energy line. So if you calculate kinetic plus potential, and let's say you get 7 joules, that's your total energy. Kinetic plus potential gets 7 joules. Draw a horizontal line at 7 joules on the axis. Your object cannot cross that line and go above it. If the object were above the total energy line, that would mean that your kinetic energy is negative. That would mean either you have a negative mass or an imaginary value of velocity, neither of which have ever been observed. Thank you for playing. All right, so let's go back to our go to it. So I just summarized here that this is the mass and that's a potential energy function, but I'm going to use the graph instead because that's easier on me, right? So what's the minimum initial speed to make it over the hump? So here's what I'm thinking. I'm thinking that to make it over the hump, this object needs to have at least 20 joules. Look over here. So the hump is as high as 20 joules. So my total energy line has to be at 20 or higher. In fact, if the total energy line were right at 20, then what the object would do is it would come up and it would just kind of come to a stop right there. So I need my total energy to be just slightly above 20, 20.001, okay, right? So I'm going to say K plus U has to be greater than 20 joules because that is the highest that I need to go to make it over the hump, right? So then I plug in my starting potential energy. So I start with 2 potential energy and my starting kinetic energy. I don't know what that kinetic energy is, but I'm going to use it to solve for the velocity. So I start with 1/2 mv squared kinetic energy, start with 2 joules potential energy. I better keep that total any number above 20. So let's subtract the 2 over. And now I've got 1/2 mv squared better be better than 18. So I'm going to multiply by 2. That becomes 36. I divide by the 9, which is the mass. That becomes 4 square root. And my speed has to be at least 2 meters per second. Exactly 2 meters per second. And we come up and we just stop at the top. Anything less than 2 meters per second, we come up, we stop, and we roll down before even making it to the top of the hump. Anything over 2 meters per second, we're going to come up. And then we're going to go back down. So now I want you to think about this. What is it going to look like when this object goes up and down? Like what's the motion going to look like? Okay, I'm going to ask you that in a moment, but let's do part B here. Describe how the magnitude of the acceleration changes from 3. So we've just crested the hump and we're going to go down. So describe, meaning use words. So here's what I'm thinking. I'm thinking that acceleration depends on force, and force is the slope of the graph. Okay, so if you're going to ask me to describe acceleration, I'm just going to describe the slope of the graph because those are going to be related. So the slope of the graph becomes more steep, then it becomes less steep. So I'm going to say that the acceleration increases, then decreases. And I'm going to try and be specific. I'm going to say that the acceleration increases when the slope is getting steeper. It looks like that's about 3.5. And then the slope decreases after that, right? Now, is it exactly 3.5? No. On this AP exam, are you going to be asked to find where this point of inflection is? Please don't. Please don't actually do that. Can you eyeball it, please? Okay. If one of these shows up on an AP exam like this one, they're probably not even going to give you the function. They're just going to give you the graph. Okay. So please don't freak out about this. Okay. Just eyeball it, will you? All right. So, and both are always directed to the right, both force and acceleration to the right, because that is the direction of downhill. Downhill beyond 3 is to the right. So the acceleration and the force and the slope all do the same thing. They become more than less in magnitude, and the force and acceleration to the right. Okay, now I want you to suppose that the object has just a little bit more velocity than it needed to get over the hump, 1% more. I'm going to ask you to do these 2 things right now. So here's some more guided practice. I want you to sketch a position versus time graph. Sketch means just give me the shape. I don't need numbers on the axes, just give me the shape for this object as it travels from 0 to 6. What would the position look like? What would the velocity look like? So just take your paper that's in front of you, do a little xt, vt, right? And just give me the shape of what they would look like. I'm going to give you 2 minutes. On your mark, get set, go. more cacophonous than I remember it being. All right, here's an animation of the object. So this is the actual object here at the top. For all we know, it's going in a straight line path. It's not actually on a real roller coaster track, but you know what? I pretend like it is. So here's like the pretend roller coaster track it's on. Look how, look how the object slows down as it approaches the high potential energy. It barely makes it over, and then it speeds up on the way down. Now, this is the actual object in real life, and then this is what it looks like on a potential energy diagram. Down here, you'll see the red graph is the force versus, and it should say force versus position, not force versus time. You'll see how the force increases as the steepness of the potential energy graph increases, then the force decreases as the steepness of the potential energy graph decreases. Notice how a negative slope on potential energy is a positive amount of force. A positive slope on potential energy is a negative amount of force because force points downhill. And up at the top, you'll see the green arrow for velocity, and you'll see the red arrow for acceleration. You'll see how the velocity slows down but doesn't reach zero, and how the acceleration increases as the potential energy graph gets steeper and decreases as the potential energy graph gets less steep. All right, did your position versus time graph look like this? If so, give yourself a pat on the head. All right, so give yourself a pat on the head. We see the object slowing down and then speeding up. All right, very good. And I think this should have some symmetry to it because the potential energy function has some symmetry to it. So if the potential energy function is symmetrical, so should your other graphs. Now, here's what the velocity versus time graph is. Strictly speaking, strictly mathematically speaking, these two graphs, the purple potential energy and the green velocity versus time graph, strictly speaking, are not the same shape. However, they will always look like the same shape, but with velocity flipped over from potential energy, right? So they're not strictly speaking the same graph. You got an object, its mass is 4 kilograms, it's at x equals 6. I give you the potential energy function, but really I'd rather you look at the graph rather than the function. So here we go, part A. What are the minimum and maximum positions farthest left and right that this object can attain? So it starts with some speed, and so how far to the right can it go? How far to the left can it go? And then I want you to describe the magnitude and direction, how they change for the acceleration as the object moves from wherever min is to wherever max is. So you got to find where minimum and maximum are. And then let's see, I want you to sketch what a force, this is incorrect. It should say a force versus position graph. So it should say sketch where a force versus position graph. I think the next slide will actually have that corrected. So you're going to sketch force versus position. You're going to sketch position versus time. And this thing is going to repeat its motion. So you're going to have 2 cycles of the motion. And then you're going to sketch velocity versus time for 2 cycles of the motion here. So hopefully I am live here. So if I'm not, then my producer, Miss Hunter, is going to tell me. So I'm going to give you 5 minutes to take a stab at this. Do the best you can on your paper. On your mark, get set, go. So I apologize, everyone. So yes, right before this example started, we did have a technical snafu. So if you're watching on the replay, then it's going to look like a bunch of video was just cut out, right? And then if you're watching live, I'm actually now on like a 5-minute delay. I'm watching right here on the live view. So I'm sorry that we're going to go over, but by the time light from this presentation reaches you, I will already be drinking an apple juice, right? Okay, so part A, what's the farthest left or right this object can go? So in my mind, I'm thinking the farthest left or right is going to be where all the energy is potential energy, none of the energy is kinetic, and the object's got to stop. Okay, so let's figure out how much energy we start with. So I'm just going to do a little 1/2 mv squared. I'm just going to say, hey, we start with no potential energy. If you start at position 6, that's 0 potential energy. Look at the graph. 1/2 mv squared comes out to 32. So we have 32 joules of total energy to start with because we start with no potential energy and all kinetic energy. So now I'm going to say, where is all the energy, potential energy? Where do we have 32 joules of potential energy? So let's look. All the energy is potential energy at 32 joules of potential energy. That happens at x equals 2 and at x equals 18. So this object is going to go as far as where potential energy is 32. That's going to be x equals 2 and x equals 18. So this object is going to roll up to 18 meters and then back down to 2, then roll up to 18 meters and then back down to 2. Okay, so describe how the acceleration changes as the object moves from 2 to 18 on its way to the right. Well, the acceleration, I'm going to say the acceleration from 2 to 6 is going to be directed to the right. That's downhill. The acceleration from 6 to 18 is going to be to the left. That's downhill. I'm going to say that from 6 to 18, the acceleration is becoming more and more and more and more stronger as the slope becomes steeper. From 2 to 6, the acceleration becomes less and less and less in magnitude. So in total, from 2 to 6, the acceleration's to the right and becoming less and less and less because the slope is getting less. From 6 to 18, the acceleration's getting more and more and more magnitude and to the left in terms of direction. Acceleration depends on force, which is the slope of your potential energy graph. Okay, so here's what the force versus position graph looks like. And I meant to say force versus position, not force versus time. You'll see when we have a really steep potential energy here, we have a very high amount of force, and that's a steep negative slope. So that's a big positive force. Remember, force has the opposite sign of potential energy. And then as the slope becomes less and less and less at x equals 6, the force becomes less and less and less and is now 0 at 6. This part of the graph over here beyond 6 is positive slope, so that's a negative force, but the slope is not nearly as steep, so that's not nearly as much force. Okay, all good. Here's what the position versus time looks like. Notice this is not a simple harmonic motion. If you watched our first video, a simple harmonic motion needs potential energy to be a parabola. This is not a parabola, so this is not a simple harmonic motion. It's an oscillation. It's a repeating motion, not a simple harmonic motion. So if you drew this correctly, you would have had the object from 6 to 18 take a long time to turn around, but between 6 and 2, takes a very short amount of time to turn around. So between 6 and 2, that's the little bottom pieces down here, the object turns around very quickly because it encounters this really steep part of the potential energy graph. But from 6 to 18 meters, it takes a very long time to turn around because that's a long way out to reaching your highest potential energy. And of course, up here, you can see how the velocity suddenly changes very rapidly because we have a humongous acceleration between 2 and 6. Here's what the velocity graph looks like. You'll see as the object travels to the right and then back to the left from 6 to 18, it takes a long time for that velocity to turn around. But then between 6 to 2 and back to 6 again, the velocity turns around very quickly. So we have a very quick turnaround on velocity from 6 to 2 back to 6, but then from 6 to 18 and back, it takes a long time for that velocity to turn around. All right, all good. So here comes example 3. So example 3 is going to be a different function. I did give you the function this time in case you care. So this object is 4 kilograms. It's at 2 again, which is the lowest point. I seem to like to start my objects at the lowest point, but this object's moving left. So think about what it's going to do. It's going to move left. It's going to stop, and then it's going to come back. So what I want to know is what minimum speed does it take for the object to go really far away and not come back and turn around. If the energy is not enough, it's going to be trapped in this thing, which is called a potential well. If the energy is not enough, you'll be trapped in this potential well. But if you give it enough speed, it'll have enough energy to go all the way to the right and be able to reach infinity. So part A, you're trying to reach a place called x equals infinity. Think about what that means in terms of this function, right? Part B, if the object has the speed you found in A, how far to the left does it go before it turns around and leaves? Part C, again, I meant to say force versus position. So on the next slide, it will say force versus position. That's what I meant to say. So sketch force versus position, sketch position versus time, assuming the object escapes and does not oscillate. If the energy was not enough, it would oscillate, but we're going to pretend like the energy is more than that. And then sketch of velocity versus time. So I'm going to give you 5 minutes for this. I'm sorry that we're going to go over because of our technical snafu, but that's okay. So 5 minutes on your mark, get set, go. got the live view going right here on my phone. So by the time these words reach you, it's probably going to be 45 after the hour. Please give me 10 more minutes of your time so we can do one more example, and then I'm going to show you where you can get some resources to review this and some other things. So it's worth it to just stick around until 55 after the hour. So what's the minimum initial speed to ultimately reach very far to the right, which is infinity? Here's what I'm thinking. If x is very big, look at this function. If x is very big, then u is just going to be 50, because 200 over huge minus 200 over huge is going to be 0. So that's just going to be 50. So in my mind, the potential energy we need to reach is 50, which means I need to start with a total energy of 50 joules. So I have a total energy of 50 joules. I start with kinetic energy 1/2 mv squared at position 2. I start with no potential energy at position 2. So then I'm just going to plug in the mass. I'm going to take the square root, and I get 5 meters per second. So it takes 5 meters per second at least to make it all the way up to infinity, right? But if I start going to the right, to the left, then to the right, then how far am I going to go? Well, if going to the right reaches me to 50 joules, then going to the left also gets me up to 50 joules. So it will go as far left as the point u equals 50 joules, which is at x equals 1 meter. So if you have enough energy to get to 50 joules going to the right, you have enough energy to get to 50 joules going to the left. Okay, here's what the force versus position graph looks like. You'll notice that when the graph is very, very steep and negative slope, that's a very high and positive force. When the graph has 0 slope at a minimum at 2, that's 0 force. When the graph is a positive slope of potential energy, then that's a negative force, and the steeper the potential energy graph, the greater the force. So the force is the most negative here, where the slope is the most positive. And then as the slope becomes less and less positive, the force becomes less and less negative. Here's the position versus time graph. You'll see that the object takes its 1 meter to the left immediately and very quickly turns around, and then just kind of travels on to the right. Just notice how it's gradually losing velocity, but it never loses enough velocity to come to a complete stop, because it has enough energy to get all the way to infinity. And then here's the velocity. The velocity starts as 5 to the left, switches very quickly to 5 to the right as the object goes from 1 to 2, and then 2 to 1, and then back to 2. So 2 to 1 and then back to 2, and the object has just reversed its velocity to positive 5. As it climbs up, the velocity gets less and less and less. Okay, last example here. This one's going to be tricky because it involves actual numbers. This is just 3 line segments, and so I tell you the potential energy in case you're having trouble seeing it here. So the object has a mass of 2. It's released from position x equals 0. The potential energy is 100 at x equals 0. At position 8, the potential energy is 36. At position 16, the potential energy is 84. Position 30, the potential energy is 0. How fast is the object moving at those 3 places? So bang out 3 conservation of energy equations quick. All the answers are integers. How much time does it take for the object to do the first piece, the second piece, and the third piece? Give you a hint. First piece is an integer amount of seconds. Second piece is something in a third of a second, right? And this last one is an integer number of seconds. I want you to do your best you can to draw a force versus position graph. Draw means putting numbers on the axes, right? A number of newtons, number of meters. Draw position versus time, number of meters, number of seconds. Draw velocity versus time, number of meters per second, number of seconds with actual numbers. You're going to get 5 minutes for this. This is the final boss. On your mark, get set, try. right, get ready for some rapid fire conservation of energy equations, because even on the replay, I think I'm about to go over time. So the total energy object, let's just look at where it starts at x equals 0. It has no kinetic energy and 100 joules of potential energy. So we have 100 total joules of energy. Now let's look at x equals 8. At x equals 8, we still have 100 joules of total energy, but look over here, 36 joules of potential energy. So then I'm just going to plug in the mass, 1/2 mv squared, and solve. I get 8 meters per second here. Now let's look at x equals 16. Still have a total energy of 100 joules, but this is 84 joules of potential energy. So then if I solve, I get v equals 4 meters per second. At the very end, x equals 30. We have no potential energy, but still 100 joules of total energy. So then that's 10 meters per second of velocity. If you got those three numbers, give yourself a pat on the head and a cookie. Now, let's see here. Between 0 and 8, how much time is that going to take? Here's what I'm thinking. I'm going to do this the easiest kinematics I know. If the speed goes from 0 to 8, that's an average speed of 4 meters per second. Now, average speed of 4 meters per second and a distance of 8, distance equals average velocity times time. So 8 equals 4 meters per second times what? 2 seconds. Takes 2 seconds to do the first bit. Now let's do it again. Between 8 and 16, that's a distance of 8. The average velocity is 6. From 8 meters per second to 4 meters per second, we got the average velocity is 6. So 8 meters, 6 meters per second average velocity, 1 1/3 seconds. All right, last bit, 16 to 30. What's the average speed? It's the average of 4 meters per second that we start with and 10 meters per second that we end with, 7 meters per second, 14 meters, 2 more seconds. So 2 seconds, 1 1/3, 2 seconds. So to make my force versus position graph, I literally take the slope of each segment of the potential energy function, and that slope is the force. The slope is 8, the force is 8. The slope is 6, the force is 6. The slope is 6, the force is 6, but with the signs reversed. Downward slope on potential energy, positive slope on force. Positive slope on potential energy, negative force is what I meant to say. So the potential energy is the negative of the derivative. The force is the negative derivative of the potential energy. So what do I do here? I make the object go 8 meters in 2 seconds, speeding up. I make the object go from 8 to 16 meters in another 1 1/3 seconds, slowing down. So it's a little concave down. Then from 1 1/3 to 5 1/3, we travel the remaining from 16 to 30, concave up because we're speeding up. And then once again, the velocity versus time graph looks the same shape as potential energy, but is not strictly speaking the same shape. You'll notice that the amounts of time are not proportional to the amounts of distance, right? Okay, so it's 0 to 8 to 4 to 10 with the amounts of time, 2 seconds, 1 1/3, and 2 seconds. All right, we're done. Here's your summary. Conservative force has potential energy associated with it. The work done by a conservative force depends on the end point, start and end, not how you got there. Force is the negative derivative of potential energy. The higher your potential energy function, the slower you go. The object cannot go above the total energy line. It cannot have a potential energy higher than its total energy, and we can use the potential energy to calculate forces, speeds, and things like that. Okay, here's some practice problems. Both of them are from 2002, one on the old Physics B exam, one on the C Mechanics exam. For those teachers who are watching, there's a really, really good potential energy function question that's on one of the secret practice AP exams behind the audit wall. I cannot reveal which the name of the file, but if you go searching for it, you'll find it. You can cut it out. You can put it in a place where only students have password access. Don't put it on the open internet. And please strip off any indication of the name of the file that it might have come from. And I think that you should be in good shape working with the College Board. If they don't like that, they'll cut out that recommendation from the video, but I've heard that they're going to be okay with it this time around. Okay. Additional resources from the Frensley Physics Facebook page. So here's how you access it. Go to Frensley Physics Facebook on Google. You don't need a Facebook account. You don't need to pay any money. You just find the page. It'll ask you to make a Facebook account. Click Not Now. Every day, 4 new problems are going to come up. One for P1, one for P2, one for Physics C, one for electricity and magnetism. They're posted at 8 a.m. Central Time every day. The next day, a scoring rubric is posted. And all these questions are supposed to be like the ones on the AP exam this year. They can be answered with only text. They don't require drawings or math to be shown. The P1 question might sometimes say that it overlaps with C mechanics. So if you're in physics C mechanics, look at the P1 question and see if it says this might overlap with C mechanics. Same thing with P2 and electricity and magnetism. So look at all the questions and see if some of them overlap with the class you're taking, right? So here's what it looks like right here. Here's the questions for tomorrow. It says AP Physics 1 question may overlap with C mechanics, but it doesn't say that for C mechanics because this one involves calculus. So that does not overlap with Physics 1, right? And then here's what the solutions look like, and they're just posted every single day. All right. Well, thank you for tolerating my technical glitch and spending the extra time with me. Those of you who did. I hope to hear from you on the Frensley Physics Facebook page. Other than that, I'll see you soon.